Hey folks, how you doing? We've got a request to take a look at this question from test two. Um, and I'm guessing that the concern was more about part B and not part A, but let's go ahead and do both parts. We're going to define the complement of G to be the graph with the same set of vertices. So this graph over here and the graph on the right have 6 vertices and the same 6 vertices. But AB is in the edge set of G bar if only if AB is not in the edge set of G. So we're not going to draw the edges that are along the boundary, but we're going to have to include all of the diagonals. So these 3 diagonals from the top vertex, and then from this vertex, and then from this vertex, and that one, and I think that actually gets all of the diagonals at that point. And so that's if this is G, then this is G bar. Prove that if G has 6 vertices, then G and G bar cannot both be bipartite. Okay. So this is going to be a proof by contradiction. Okay. We're going to assume that G and G bar are both bipartite. And then we're going to show this leads to a contradiction. Okay. Since G is bipartite, the 6 vertices that are in G can be divided into 2 sets, X and Y. Two sets, X and Y, such that every edge goes from X to Y. Every edge connects a vertex in X to a vertex in Y. Okay, so we have that so far. Now, we don't know the sizes of these 2 sets, X and Y. There are 6 vertices total, which means they could break up into a set of 5 and a set of 1, or a set of 2 and a set of 4, or a set of 3 and a set of 3. We don't know how they break up, but one of the sets will either be 3, 4, or 5 vertices. And so, anyway, one of the sets will have 3 vertices or more. And what I'm going to say here, and this uses some language that we don't use too often in this course, but we use it from time to time. Without loss of generality, assume X has at least 3 vertices. Okay. When I say without loss of generality, I know that one of the sets, X or Y, will have at least 3 vertices. And if the other set, Y, has 3 vertices, the proof is going to be exactly the same. We just have to do it for Y instead of for X. And so the logic of the proof doesn't change if it's the case that Y has 3 vertices. So X has at least 3 vertices. So 3 and 3, 4 and 2, or 5 and 1. But we're just look at 3 vertices, A, B, and C. Okay. So here's sort of a drawing here. X has 3 vertices, A, B, and C. It may even have more than 3 vertices, but it has at least these 3 vertices, and then Y has some other vertices over here. Because the graph is bipartite and the edges all go from one set to the other, AB is not in G. Because AB would connect 2 vertices in X. But then neither are BC and AC. And neither are BC and AC. Therefore, AB, BC, and AC are in G complement, because any edge that's not in G is in G complement. But if I have A, B, and C in G complement, G bar, and AB are connected together, and BC are connected, and AC are connected, that's a cycle with 3 vertices in it, which is an odd cycle. So therefore, G bar contains an odd cycle. But we have a theorem that says a bipartite graph does not contain any odd cycles. This is a contradiction. Since a bipartite graph has no odd cycles. And that finishes up the proof. Since this is a contradiction, then we cannot make the assumption that G and G bar are both bipartite, so one of them cannot be bipartite. So that finishes up the proof. All right. I hope that was helpful. If you have other questions, let me know, and I will try to write some more videos. And good luck on not just this final, but everything else you've got on your plate this week. All right. You take care.